All right, it seems like folks are joining in over here. Hey, good morning, Piyush. Good morning, Vibha again. I hope you guys are doing good this Sunday morning. So, how are the rains now in your city? Is it better now? Okay, great. All right, so seems like Sudipto is joining in as well. So, did you guys try out something from what we learned yesterday? Did you guys try out something with Skykit Learn? Did you got a chance to explore something? And first of all, has any one of you worked with Skykit Learn before? So yesterday we just saw a glimpse of what you could do with Skykit Learn, and we were able to build a very simple model and our first learning model using Skykit Learn. But were you guys able to explore something more in terms of what you could do with Skykit Learn? Okay, that's fine. And I'll make sure that you have enough assignments so that you know what needs to be tried as well. So today I'll try to again make sure that you have an assignment for you to work on. But again, it is fine that if you have missed out a few assignments before, you can keep working on them on the side, but start working on the new assignments as well. All right, so seems like we are on time and let's get started for today's class. Again, this is our second class in the machine learning module, the supervised machine learning module. And we are going to go over what we call as naive Bayes classifier today. So the problem that we saw yesterday we discussed two types of problems. What were they? What were the two types of problems did we discuss yesterday? So let's do a quick recap over here. So what were the two types of problems that we saw that in machine learning we come across? What are the two categories of problems that we saw? So Sudipto, these are the approaches to solve a problem, right? So the two types of problem, overall we said that there are two types of problems that one might come across. The first one is regression problems and the other one was classification problems. And yesterday when we were doing the student score prediction, was it a regression problem or was it a classification problem? We're trying to predict the score of a student. Yep, it was a regression problem because the score over there was a continuous valued output, right, which was dependent upon the hours that a student studies, right? So the score was continuous and we said that this was a regression problem. And in our today's class, we'll try to solve a classification problem, okay? And yesterday, the model that we used, what was it called? What was the name of the model that we used yesterday? Yes, linear regression, right? And why is it called linear regression? Why is it not polynomial regression? Or why is it not parabola regression? So not just because we are using a slope and y-intercept, right? The answer to that is that we assume that there is a linear relationship between our parameters and the target value, right? So we were assuming that there exists a linear relationship. So let's say if I have a point like this over here, right? So there we have a curvy point over here, right? So these are curvy points. So all our data sets are separated in a curvy, it's not so much linear. But even if you try to do a linear regression on this one, the linear regression model will always try to fit a straight line over here, right? So it will always try to fit a line, or no, if it is 3 dimensions, you will have a plane, right? So we are always assuming there is a linear relationship between the parameters and the target value. And that's why we call it as a linear regression model. It is not always accurate, but it is good enough for us to start with. Okay, does that make sense? What else did we study about the linear regression model? When we say that we are trying to build a model, what are we actually trying to come up with? When someone says that I am building a machine learning model, and especially supervised machine learning model, what are they actually trying to come up with? So remember, we had something like this. We have the data, we have a function, and we have the output. So when someone says I'm building a machine learning model, what are they trying to come up with? Yeah, the mapping function. So we say y is equals to f of x, right? And if you want to be mathematically more precise in terms of notations, you should always use a small y over here and f of capital X. Now, a capital X over here means that this is a vector, because x could have multiple elements in it, right? So 2, 3, 4, 5, based on all the features. So this is feature 1, this is feature 2, this is feature 3, feature 4, and so on. So when we say y equals to f of x, this is the expected output. This is the input data. And this is the mapping function that we are trying to find out. We are trying to find out what is the f that might have resulted in the expected output. Does that make sense? Now, is it fresh in your head now? Okay, great. All right. So then we also see some different ways of classifying machine learning algorithms even more, right? So because you could describe the same things in different categories. So you could describe, let's say, a man as a bipedal animal, but we could also categorize humans as maybe they are vegan or they are non-vegetarian, right? So there are different ways of looking at the same thing, and you could categorize machine learning algorithms in different ways as well. So one way we have seen is what approach do they take. One way we have seen that whether they are trying to come up with a continuous valued function or whether they are trying to come up with discrete valued function. So another way we'll see today on how do you categorize a machine learning algorithm. And then we'll build the naive Bayes classifier as usual. After we, the first thing that we'll do is try to get an intuition behind naive Bayes classifier. And once you have the intuition how it works, then we'll go in and build that naive Bayes classifiers in scikit-learn. So we won't be building it from scratch, but we'll be using scikit-learn to build our naive Bayes model and then perform classification tasks on it. So just one thing I want to make sure that you understand, that in our yesterday's class, we have studied a little bit of linear regression. And there are other types of regressions that are commonly studied whenever you take a machine learning class. There are other forms of regression as well. Has anyone heard of any other form of regression? So the logistic regression over there is kind of a misnomer over there. Even though it is a regression, it's not really regression. It's a sort of classification. So the term over there is confusing as such. But yeah, there are other ways and ways to formalize the linear classification model as well. And we are going to go over those things when, yeah, so Sudipto has that right over there. So we have other forms of linear regression, lasso, ridge, and so on. But we are going to go over them one step at a time. I don't want to bombard you with all sorts of regression at once and do all the math behind it. But our approach, as I said, is always to first make sure that you are hands-on with the tools that you want to use, and then slowly we'll uncover a lot of things and know the details within those things. So just like I had mentioned before, if you are studying a book, this is your book approach, wherein they'll show you linear regression 1, linear regression 2, linear regression 3, and so on. But the way I like to approach this problem is to show you a little bit about linear regression. Then we'll do a little bit of classification, right? So that now you know a bigger picture, and we'll do some other stuff as well. And after we have covered a little bit, we have covered some breadth, we'll go one step even down. And then we'll explore the math behind the linear regression as well. Then we'll do how the line fits, because when we were doing this yesterday, our line was getting fitted without even us knowing, right? So scikit-learn was doing a lot of things in background. So how does this line actually come in? So we will use gradient descent, and so we'll see how to use gradient descent for linear regression as well. So don't think that we are done with linear regression and we are moving to classification. It is just that we'll now see some of classification, we'll see some of other concepts, and then come back to linear regression and the math behind it as well. Okay, does that make sense to everyone? And we have already discussed this as in our I guess the orientation session, where I was talking about the top down versus bottom up approach. So everyone with me on this one? All right, so again, a little bit more revision. Supervised machine learning, we have said that what are these things called over here? So when I have a supervised machine learning model, I want to learn from examples, right? So what are these things? What are these called? Yep, these are the features based on what I am trying to predict. And what is this over here? The output that I'm trying to locate. The target variable, that is correct. Okay, so this is the target that I'm trying to predict. And these are the gray cells over here. These are what set is it? Is it training or is it testing? The gray cells. Yeah, this is my training data. And these are the things that I'm trying to predict. And these are my test data points. Okay, so in supervised machine learning model, we saw that we are given a set of examples and we learn through examples to find predictions and to interpret things about things that we don't know. Then we went and saw the linear regression model. And when we create a model, the first thing that we want to create a model over here, and creating a model is actually coming up with the two coefficients. Which are those two coefficients? If someone says that I want to create a model, what are the two coefficients in a linear regression model if it is a two-dimensional setting? Yep, the two coefficients that I want to come up with are the m and the b. So I can say y is mx plus b, and because once I have the equation of the line, you must remember, just like when we did 2x, y equals to 2x, right? So when we had solved the quiz where we got the answer as y equals to 2x for that line, if x was 20, was it easy to get the value of y? Because if we have the value of x over here, if I say x equals to 10, can I get the value of y, corresponding value of y now? Does that make sense now? Let me know if I'm going too fast. I'm just trying to revise the things that we have already covered yesterday, and I want to have those things fresh in your head. So our predicted score in this case, visually, we can just say that this is 60 marks. So Piyush, over here, I was talking about an example that we had done yesterday, a quiz that we had solved, wherein I had asked you, what is the value of y for x equals to 20 on that line? Right? So not this particular line. Over this line, I don't know what the exact m and b is. But in that line, which in the quiz that you had solved, you had something like this. M equals to 2 over here, and the b was 0. Right? And the equation of that line came up to be y equals to 2x. Do you recall this? Right? And what I'm trying to point out over here is, once you have the model of the world, once you have this equation, getting the prediction is equivalent to just putting in the value of x and getting the value of y out of it. Okay, so it is that simple. So that is the reason whenever we are doing machine learning, and a lot of these times we are not generally worried about the performance of our predictions, right? Generally, when we talk about machine learning, we are worried about the training time itself. Okay, because sometimes if you have that equation, computing that is a piece of it's a cakewalk, right? Once you have that equation, getting the predictions is easy. The tough thing or the time consuming part is the finding those coefficients. How do you get the m and the b or the whatever parameters of the model are? So sometimes finding these models, the model itself might take 2, 3 or even more days, right? So depending on how complicated of model that you are building. But once you have that model, it is instantaneous to get the equation, the value of the equation out of it. Okay. So building the model itself is costly, but prediction is just solving an equation, and so it is very quick. So difference between our predicted and actual value, we said this was the error in our prediction, and we want to reduce as much of error as we could. So this is something that I would want to start off with today. This was, until now we have just seen we just revised whatever we have done yesterday. Okay, I wanted to have all of those things fresh in your head. So categories of machine learning algorithm, and again, as I said, you could categorize the same thing in different forms. Like a human, you could call us as bipedals, or we could also think of us as vegetarians versus vegans versus non-vegetarians, and so on. So machine learning algorithms, you could look at it in different ways as well. In this category, what I'm trying to categorize them, in based on the approach that they take in terms of coming up with the decision. So in that sense, there are two types of machine learning algorithms. The first are the discriminative algorithms, and the other are generative algorithms. And let's see the approach that each of these take while solving a machine learning problem. So a discriminative algorithm, what it does is, this is the same example that we had yesterday. So this is the same example that we were looking at on yesterday. On x-axis, I have the movie time. On the y-axis, I have the IMDb rating of the movie. Now I'm trying to figure out whether the user will dislike a movie or like it. Okay. So a discriminative algorithm, what it does, it looks at both of these training data set labels, both of these labels. It will look at all the points in one instant. And what it will do is it will try to classify or come up with a line which is best separating both these classes. So here's how a discriminative algorithm will work. So it will try to draw a line first. Okay. So just like we did yesterday, y equals to mx plus b. So it will try out some value of m and b. Okay. Then it will see whether I'm doing a good job. Over here, it will see that this line is not so good because still there is some point which is outside of which is on the other side of line, which is still, now there is some misclassification happening over here, right? So most of the points are on below the line, but there is some red point which is still getting mixed with these green points. So there is some misclassification happening. So it will adjust its line. Our algorithm will say, okay, let me adjust m and b such that we don't have a lot of misclassifications. So it will try this now. And it says that it seems a little better, but there is still one point on the other side of the line. So it will try one more time. And now with this line that we have come up with, it seems like everything is correctly classified. And in that sense, we could say that a discriminative approach over here will try to do some sort of trial and error, and based on which it will come up with a decision boundary. So one thing you should note about discriminative algorithms is a lot of times it will ignore most of your data set. So do these 3 points over here. So look at these 3 points, these 3 red points that I'm highlighting. If I take them away, imagine that these are gone. And let's say if these 3 points are gone as well, will your answer to the discriminative algorithm change? Does it even matter? No, right? Because in most cases, what the discriminative algorithm cares about are the points on this decision boundary. So these 2 points and these 2 points are the most contributing factors in this decision of drawing this line. Okay. So what is happening over here is, even though we have a lot of training data set, discriminative algorithm will decide its boundary based only on the edges which are very close to each other, the corner cases. But in practice, what we know is, and again, discriminative algorithms are one of the most powerful algorithms out there. So any, let's say, neural network or the gradient descent algorithm that you will study going ahead in the class, it is a discriminative algorithm. But as we know that it only takes care into account only few points which are close to each other, what we need to give what discriminative algorithm needs is, it thrives on a lot of data. Okay, so if you give 10,000 points, maybe you will have 100 points which are very close to each other, and now discriminative algorithm will perform very good. But if you give it only 10 points, maybe only 2 or 3 points make sense, and the decision boundary that you are come up with, it might not be so good. Okay, so discriminative algorithms, do you need a lot of data, or do we need less data? So from based on what I have said, do you think discriminative algorithm needs a lot of data or less number of data points? Yeah, a lot of data, because even after you have 10,000 or even more points, then it will just consider few hundred points which are very close to each other, and based on which we'll create a decision boundary. Okay. So the other approach that some algorithms take is called as a generative approach. Again, I'm showing you the same example over here. In this case, what our algorithm will do is, first just look at the points which are labeled red. Okay, so we don't want to even look at the green points. We'll just look at the red points on this space over here, in this two-dimensional space. So we know, because in a training data set, we already know which are the movies that the user doesn't like. So we just look at these points, excuse me, and we'll try to come up with a region in the space which best describes this set of data. Okay, so just like we were doing, we were drawing a line yesterday. Similarly, we could also describe this space in form of a curve, or we could come up with a sphere in this space which describes this, these points, where these points are lying. Okay, then what we do is, then we look at only green points now, and we say, okay, let me not look at red points, let me just look at all the green points. And based on all the green points, looks like all my points are lying in this region. Okay, and I store the information about this region, may it be in the form of a curve, or you could always describe a set of equation which is describing this boundary, right? So based on these two things, I have saved in my memory, in the model's memory, I know which is the region where the green points are, what is the region where the red points are. Okay, and note that this is, if behind the scenes, it is relying upon how many number of points are occurring as well. It is not only seeing which are the two corner cases over here, but it is also looking at the number of points in that space. So in some sense, there is a notion of probabilities associated with generative algorithm. So a lot of algorithms that you would come across, such as naive Bayes, and these are generative algorithms which rely on the probabilities of the points occurring in your data set. Okay, and now let's say if I take away all my training data points, now all you have left is the model that we have created in our world. If someone gives you this point in this space, can you now tell, will the user like it or dislike it? Yeah, the user is going to dislike it, because from the model that we have created in our memory, we know that everything around this red region are the movies that the user doesn't like. Okay, and again, this is not just one approach. What you could also think about is, what if this blue point is lying outside the red region and the green region? In that case, what would happen is, yeah, so Nitesh, that is something that I was just talking about, is what if the point is not even in the red region or in the green region? In that sense, you might want to know there will be some, again, probabilities associated with it. So you run your data set from the first classifier over here, and it says that there is, I think there is 40% probability that, or even 30% probability that it is close to me. Okay, so this red region over here, this first classifier over here will say that I think there is 30% probability that it is, the user is going to dislike it. And maybe over here, this one, because this point is a little bit away, imagine that my point is where my pointer is, because it is a little bit away from the green cluster, it will say, I think it is 30% probability that the point is in the green space. Now, based on that, what will you as a machine learning engineer do? If this red region is saying that there is 40% probability that it is in my area, and this green region is saying that there is 30% probability that it is in my region, this model is saying that this is 30% probability. So which one would you pick? Yeah, so what you as a machine learning engineer would do is, because over here we are saying that this is maximum likelihood that it is in this region, but outside this region you will still get some probabilities associated. Okay, so all the, in the sense that this entire region is mapped as such. Okay, over here it is most confident, so in this region it is most confident that it is dislike, but outside this region as well, there is no hard and fast decision boundary as such. At every point in this space, the model is going to come up with probabilities saying that whether the user will like it or dislike it, and whichever probability is more, you will pick up that one. Does that make sense? And we'll see an example doing that with naive Bayes. At any point in space, there is not just this closed region. At any point in this space, you will get probabilities out of this model. The probability of the user liking it and disliking it. Whichever probability is more, we'll pick that one. Does that make sense? Okay, great. So example over here, linear regression is an example, gradient descent is an example of discriminative algorithm. Naive Bayes classifier that we are going to see today is an example of a generative algorithm which relies on the probabilities of the points over here. Okay, so it's not just relying on the decision bound, the points which are at the decision boundary, but it is relying on overall on the points which are in this space. So a lot of times, can you think about why discriminative algorithms might be a little bit more faster than generative algorithms based on whatever I have said? So discriminative algorithm generally is computationally more efficient than a generative algorithm. And why do you think that might be so? So a statement that I'm making is a discriminative algorithm is generally more time efficient than a generative algorithm. Yeah, that is true, because we are anyways just concerned with the decision boundary cases. And once you know what these points which are on the decision boundary, and how do you know which points are on decision boundary, how do you not know? We'll see then when we go into the gradient descent class. Okay, because just to give you a hint, the derivatives over here will be maximum when you are on the decision boundary. And over here, in the generative case, we also need to associate probabilities with each case. Over here, when a movie is over here, your model will not give you an output as what is the probability of the user liking or disliking. The only thing that it knows is the user is going to dislike it. There is no probability associated over here. Over here, we are interested in the probabilities of these things. So calculating those probabilities initially is difficult, and coming up with this space itself is computationally not so efficient. Okay, and not just about the sphere or the line. It's not about the shapes as such that I'm talking. Over here as well, you can just think of it as just one line passing through the center. It doesn't have to be just the sphere. But what I'm trying to describe is the probabilities in terms of looking at each point versus just looking at points which are on the borders. Okay. All right, so let me give you an intuition behind how naive Bayes algorithm works. And again, I don't want to go into I would say the Bayes algorithm, the Bayes equation itself. Okay, so if you go online and search for Bayes equation, we have studied those things in our high school class, maybe in our 12th or even in our engineering schools. The Bayes theorem, right? Everyone heard of Bayes theorem? The probability of event occurring given something else occurring. Okay, so I don't want to go over the Bayes theorem itself. What I want to show you is how that could be applied to solve some machine learning problems. So over here, I'm giving you an example of from the Titanic data set, and that is a data set that we'll be working on today as well. Okay, so let me show you what is happening on your screen over here. There are two classes of passengers, the one who have survived and those who have not survived. And we have people traveling in first class and second class. We have some males and female passengers. Okay, so these are the categories that we are looking at. These are the features: the first class, second class, whether they are so these are the features, which class they were traveling and what were the gender, right? So whether they were male, female, and so on. Now we know the outcomes of the Titanic event, right? So we know which passengers survived, which passengers didn't survive. So what we could do is look at all the passengers and come up with these numbers over here. So let's say if this is the overall probability of a passenger surviving and not surviving. So over here we are seeing that there are 50-50% chance. So can we come up with this number 50-50? Can you think of how someone could come up with this 0.5, 0.5? So what I'm saying over here is overall the probability of surviving is 0.5 over here, and overall the probability is 0.5 over here as well. Can you think of how would someone come up with that number? It is pretty straightforward. And can you tell me how will you come up with this 0.5? So we have the facts of the event. Yeah, so obviously Sudipto says that you just look at the people who survived and divided by total number of people who were there in the ship, right? Or total number of people who were survived plus not survived. Yeah, assuming that that is the total set of people, right? There is nothing in between. There is nothing like partial survival. So if there is like people who survived divided by total number of people in the ship, this will give you the probability of surviving. And over here you say that total number of not survived divided by total number of people on the ship, that will give you 0.5 as well. So what we are saying is, again, this is not the exact numbers. I'm just giving you some simple numbers so that it makes sense for us to make in the head, so that it's easy for us to do these calculations in head. Okay. All right. And similarly, you could come up with these numbers for first class, second class as well. You could think of how many people were traveling in first class and who survived, and then divided by total number of people traveling in first class, right? So that's how you will come up with all these numbers. So let's say we calculate all these numbers, and now the question someone asks us is, given a person who is a male, will a male traveling in first class, will they survive or not? So can you look at these numbers and intuitively come up with what might be the answer? You don't even have to do any calculations. Just think about, based on these numbers, will a male traveling in first class survive or not? And again, not just don't give me number of the chances, just give me, will they survive or not? That's what I'm interested in. What will be your prediction be as a machine learning engineer? And again, as I said, doesn't matter what chances what are they. Can you tell me, will they survive or not? And what will be our prediction as a machine learning engineer? So most of you say yes. Intuitively, we can see that it is a yes, right? Because the way you should go about looking at it, first thing that we know is they are a male passenger. So we come over here and we look over here. Okay, the male passenger, the chances of surviving are 0.5 and the chances of not surviving are 0.5 as well. So right now we are still not sure, right? Then we look at another piece of information that is available. So we also know that they are traveling in first class. Okay, so we look at first class over here. Seems like chances of surviving in first class are more than the chances of not surviving, right? In first class, we know that people have survived more. So intuitively, we say that, and overall also it is 50-50. So we don't know that, right? So intuitively, we know that everything was 50-50 until we came to a point where we know that they are in first class, and because they are in first class, there is chances of surviving are more. And that's why our machine learning algorithm, what we should predict is the chances of surviving are more, and that's why we'll predict that the passenger has survived, right? And if you want to formalize it, this is how you would do the math. What you would do is take the chances of them surviving in first class, multiply that by them being a male, and then multiply with the overall probability over here of surviving, and that will give you the likelihood of 0.15. If you do this over here in not surviving, because they are a male, we got because they are in first class, not surviving is 0.4, this male 0.5, and this 0.5 coming from the overall probability of not surviving. So if you multiply that, you get 0.1, and because 0.15 is greater than 0.1, because 0.15 is greater than 0.1, our prediction will be that this passenger will survive. Okay, does that make sense to you? How is this working internally? Naive Bayes algorithm, what it will do is first calculate all these numbers. Remember that it's a generative algorithm. So first of all, it will try to come up with the probabilities and associated probabilities. Then it will calculate the chances of them surviving and not surviving, whichever is more. Right? As Nitesh was asking, what happens if there is in between? And what I said was, there is no such close circle as such, but at each point you will get the chances of them being in one class versus chances of being in the other class. Whichever is more, you will take that answer. Okay, so let's do one more example so it is clear. So one more example over here. Now this is a email spam classification problem, and this is something that you will be doing in your homework. Okay, so we'll be doing this in your homework. I'll be giving you a data set of classifying emails as spam or not. And what you could do is look at the words which are mentioned in this email, and depending on what we have seen in the past, we could come up with the probabilities and the likelihoods of them being a spam or not a spam. All right, so over here we are seeing that the overall probability in our data set, the chances of an email being a spam is 0.6, and the overall probability of chances of being them not a spam is 0.4. Okay. Within the spam emails, we have seen these three words. Let's say our entire dictionary of entire corpus has only these three words: money, lottery, and code Hiroko. And obviously this is not realistic. We'll have many words in a text email corpus. But for the sake of simplicity, let's say we have just these three words over here. What we know from past in our data set is in our emails is that whenever the word money has come, there is a 60% chance of it being a spam, and there is only 30% chance that it's not a spam. Okay, and you don't get confused by the numbers right now, because 0.6 and 0.3 are not adding up to 1, right? Don't focus on them. I just want you to compare the probabilities right now. Lottery, it seems like 0.8% chance of them being a spam, because it is highly likely that if there is a word lottery in it, the word is a spam. And if the word code Hiroko is in your email, there is very less chance that it's a spam, right? We don't want our emails that are coming to you to go to the spam folder. So Code Heroku, very less likely that it's a spam. And similarly for not spam as well. Overall, we have more number of spam emails than not spam emails. Now, can you find out if you see these two words in your email? If I send you an email with Code Heroku money, is this a spam or not a spam email? Yep, so most of you are getting it correct over there. If you do the math, we'll see Code Heroku money, right? So Code Heroku 0.6, overall probability 0.6, spam over here 0.01, and money is 0.6 as well. So 0.06, 0.1, 0.6. This will give you 0.036. And over here 0.3 because we have money over here, and 0.95 for Code Heroku not being a spam, and 0.4 over here, the overall probability of not spam. Overall, we could see that 0.114 is greater than 0.036. So we'll label, our prediction will be that this is not a spam email, because what we see is because Code Heroku has a very high probability over here of 0.95, this number has got a little bit much more bigger than this number, right? So this is the most contributing factor over here because of the word Code Heroku. And the probabilities of it not being a spam in the past, we see that this number has now become a little significantly more bigger than this number. Does that make sense? Does that give you intuition behind how naive Bayes algorithm works? First thing it does, it first, based on the supervised training example, it is a supervised learning algorithm. So first it comes up with all these probabilities. Because it's a generative algorithm, first it will look at each word and then associated probabilities with each word. And once we have these words and these probabilities, now calculating those, predicting is just mere a fact of multiplying the overall probabilities together. Any questions on this one? Anything that you thought I went a little bit fast over there, or you think that it was not clear on how are we making this decision? Why does this thing work? So it's a logical approach, right? It is not so, there is no rocket science to it as such. All we are saying is we are counting the probabilities of individual items, these, you could think of them as individual features of your text, right? So this one word, Code Heroku, is one feature. This is your second feature. And we are counting the probabilities based on these features that are occurring in this text. Okay. So a big assumption that we are making over here, and now let me ask you if you can get it by yourself. So what is a huge assumption that we are making in this case? And what is something that we might be ignoring? And that is the reason, that would give you the reason why the naive Bayes algorithm is also called as naive, right? So why is naive Bayes called naive? And the reason for that is there is a huge assumption that we are making while we are doing all these things. Can you think of that thing? Okay, so over here, no, when we multiply probabilities together, you would know that no, based on whatever we have studied probability in our engineering schools or no back in our high school, is that no, you could multiply these probabilities when these are independent events, right? So if the chances of money occurring is independent of the chances of the lottery occurring in that email, that is when you actually multiply those three things together, and that is when it makes sense mathematically. Over here, do you think there is some correlation between the word money and lottery? Is it highly likely that these two words are highly correlated and these are not independent events that we call in terms of probability? Do you think this is independent event, that chances of money occurring in an email, is it an independent event as the chances of lottery occurring? Are these independent events, or there is a huge chance that they are highly correlated? They are highly correlated. It is most likely that these words money and lottery are highly correlated, and we are making a naive assumption. We are treating each word as an individual feature or a vector over here, whereas it is not that case. And that's what naive what makes naive Bayes algorithm naive, that we make this assumption that everything in our word, each word is independent of each other. Even if the code Heroku word comes at the first position, or no, it occurs in the last position in that email, does that even make sense? So let's say if this code Heroku money over here, will our answer to this differ if we have money first and code Heroku later? So the order of these events also we are not taking into any account, right? So maybe if I'm sending you an email with saying lottery money and then just saying my word code Heroku in the signature, maybe it's a spam email, right? Because the order of these words also matter. And over here I'm just saying that nothing matters to me. All these are independent events. I can just multiply all the probabilities together. So do you get a sense of why naive Bayes is so naive? Okay, great. But there are significant advantages of naive Bayes algorithm, and that's why it is used in practice a lot of times. So it is simple and easy to implement in terms of other generative algorithms. If you look at them, compared to them, it is relatively easier to implement, and it is because it's a simple, not just in terms of simple to implement, but also it is time and space efficient compared to other stuff, other generative algorithms. It executes quickly. As I said, no, even though generative algorithms in general are less time efficient, the calculations that we are doing in naive Bayes, they are not rocket science. We could do them in our head pretty quickly as well. And it scales for real-time use cases and massive data sets. In a lot of these cases, when you are doing email spam classification, you are dealing with gigabytes, terabytes of data. So you want an algorithm which is very quick, and it doesn't have any things like gradient descent, and those things will take a lot of time to execute and find those boundary cases. So if there is a real-time use case where you are trying to rebuild your model every second, in that sense, if you're trying to learn from new examples, if you're trying to build a model which is online, in that case, naive Bayes algorithm is a good choice of an algorithm. Even though it might not give you that much of accuracy, it does scale for real-time use cases, and especially when you have large number of features. In an email, let's say if I have 10 words, right, and if I have 10,000 emails, how many total number of features do I have? Or let's say, to put it that way, if in my entire Wikipedia, let's say if I am trying to scrape Wikipedia, and if I say that in Wikipedia there are 100,000 words, or in my entire corpus of Wikipedia dataset I have seen 100,000 words, then how many features do I have? Yeah, 100,000 features, right? So if you have so many number of features that you're dealing with, and in that case, naive Bayes algorithm is a good choice. Again, a quick quiz to make sure that everyone just understood whatever I just told you. Naive Bayes algorithm is best suitable for cases where Yep, where the speed of algorithm is critical, where you don't care that no, you don't want to get the best result. If it was something where no, it will predict whether you will know this patient has a cancer or it does, they don't have a cancer. That's you shouldn't use naive Bayes algorithm there, right? But if you're trying to recommend movies to a user or classify a spam email, in that case, it might be okay. Even if you give a wrong recommendation, nothing bad is going to happen to that user. Okay, he might just waste 2 hours, but if you're recommending a bad movie to a user, that is fine. But don't tell a patient that he has a cancer using naive Bayes algorithm. Okay. All right, so I think we already have this environment set up for us. So let's go ahead and work on our Jupyter notebooks. We'll use this data set which is given to us. So let me go over here and give you this data set as well. So the first thing that I want you to do is open up your Jupyter notebooks. So let's come over here. We'll be working with the Titanic dataset example that we just saw. So go to your Jupyter notebooks, go to notebooks.azure.com. I've already signed in over here. I hope by now everyone has an account on Azure Notebooks. And let's create a new project over here. So I'm going to say my projects, new project, and I'm going to say naive Bayes classification. I'm going to make it public. Okay, let me know once you've created a new project. Let me also create a new notebook over here. I'm going to say NB Python 3.6, NB for naive Bayes classifier. And let me know once you have created your new notebook and you are ready to go. All right, so let's just wait another few seconds to make sure that everyone is ready. Right, so the first thing that I want you to do is also make sure that you have the data set downloaded. So let me give you the link to the data set, and I want you to go ahead and do it just like the way we did yesterday. So look at your yesterday's notebook example and go ahead and do that. And I'm already showing you the answer over here, so I shouldn't do that, but you should get a sense of how you should do it. All right, so here's where your dataset file is located. So I want you to download this dataset inside your Jupyter notebook from this dataset. You have already done this yesterday using the shell command curl, right? So you could send a curl request to this CSV file and download this CSV file in your cell, okay? A non-programmatic way would be to download this on your computer, then go over here to project. You could also say upload and upload from computer. You could do that as well. But if you want to just do it in the Jupyter cell itself, you could do it over here as well. Okay, so go ahead and do it. And let me know once you have downloaded this data set in your Jupyter notebook or in your project. All right, so let's wait for other folks as well. So Himanshu, are you able to open this notebook itself, or try clicking on this button as well? So try clicking on this restart and run cells, or do you don't see this entire thing? Are you not seeing this tab itself? If you have the Jupyter notebook locally, so what you might also try to do is either just create a new project. Something might have gone wrong with the project. So just create a new project and try another notebook over there. Try to do that first. That is weird if Azure Notebooks is not working for you guys. The reason why I was using Azure Notebooks so that everyone is consistent and everyone does get the same kind of results. Because a lot of times we see that with the difference in environments, sometimes what I see that you might not see and those kind of things. That's why I wanted to make sure that we use Azure Notebooks. That's weird. So Nitesh says just sign out and sign in. Himanshu, try that one out. So sign out and sign in and see if that works. One of my colleagues used to say that Microsoft will always surprise you. Whether it works or not, I don't know, but Microsoft always tries to surprise you. So again, Google Colab is also another option, but in my experience, it hasn't worked that well for me. And especially, it is significantly more laggy as well than what I've seen. If you, just for everyone else to know, Google Colab is also another option where we could run our GPU enabled notebooks in the cloud. So if you want to try that out, feel free to try it out someday. And everyone has their own preferences. So if you feel that Google Colab works for you, feel free to use that as well whenever we are using Jupyter notebooks. So Nitesh, the CSV files, we have to put it in the same folder where our project is. And what I asked you to do is try to do it programmatically. We have already done this yesterday. I'm not sure if you were there yesterday or not in the class. So what we could do over here is send a curl request from within our Jupyter notebooks to the CSV file and get it inside our folder. So what you could say is, for those who were not there yesterday, you could simply add an exclamation mark, and any shell command that you could run on your Unix shell, you could run it from within your Jupyter notebook as well. Okay. So I could say curl, then give my URL where my file is located, right? And then say the name of output file O as titanic.csv. Okay, so this will download the CSV file from this location and put it inside our folder and call it titanic.csv. Okay, so let's run this, shift enter. And now we have seen that we have downloaded it 100%. Let's make sure that it is present over here. If I refresh it, now you see that titanic.csv is in my same folder. And as I said, if you don't want to do it this way, you could always go over here, upload it from your computer as well once you have downloaded it. Okay. So we have our CSV file now. Let's go ahead and import our favorite package. And that favorite package, at least for me right now, is pandas. Okay, so I'm going to import my favorite package right now. So just import pandas as PD. And let's just import matplotlib as well. So import matplotlib .pyplot as PLT. Nothing that we haven't done before in our class, right? Matplotlib. Okay, so it might take a few seconds because it is building those caches for the matplotlib, but now it is there. Okay. All right, so go ahead, read your CSV file in your Jupyter notebook. Nothing that we haven't done before. So step 1, read your CSV file, dataset in our program. Go ahead and do that. Use pandas to read your CSV files and get your data frame ready. Okay, so Vibha is done. All right, so pretty straightforward, right? We've done this so many times before in the class. We could simply say df is pd.read_csv. The df is for our data frame over there. Let's give our file name Titanic .csv. Okay, and let's see what do we have. So df.head over here. All right, so seems like we have some columns. Survived, the class of the passenger, which could be first class, second class, third class, the name, their sex, gender, their age, whether they have any siblings or spouses abroad. Well, this is an interesting column for us to look at. Parents or children abroad, and what was the fare, right? So what was the fare of the ticket? I don't know if this is in euros or USD, but seems like the bigger the number, that would mean that they have paid lot more money to travel on the ship. Okay, and our job will be to find the correct predictions for the first column over here, which is survived, whether they survived or not, by looking at all these features. Okay, so from this setting over here, from whatever you know about the Titanic accident, can we just brainstorm a few things about what features make sense over here and what features might not make sense? So first of all, again, simple exercise. What is the target and what are the features? I just want to make sure that our lingo is common between both, like between me and you guys. And when I say features, you know what I'm talking about. And when I say target, you know what are we talking about? Yeah, survived is the target column. Everything else is the features. And my question to you is, what features make sense over here and what feature might not make sense to predict whether someone has survived or not? So yeah, the gender, the sex over there, the age, the whether they have parents or children abroad, and even the fare of the ticket, right? So Vibha, why do you say that the fare of the ticket won't matter? So from what we know about the Titanic accident, you know that the people who are rich, they were able to get out of the ship much more faster than the folks who are in third class or even the workers, right? So in that case, the fare of the ticket might make sense, and the people who are rich, they might have been able to get out of the ship much more quickly. Okay. So based on this, let's we'll try and remove this. And what do you think about the name over here? Should we even keep that in the features? So Sudipta says yes. And why do you think so? So if there is a person called John, whether he is in first class or second class, how does that name matter? Well, yeah, you could always make such argument saying that and if you look at the data set, we don't have any you know doctors or those kind of things in the data set itself. But again, the name as such would be the something which would matter least, and it would create more noise in the system than it would add. Or the benefits are worse than the noise that it would create in the system. Okay, and that important person, we don't know whether John is important or Jim is important. So we don't have a list of associated dictionary of what names were important. Okay, so what I'm trying to tell you is names maybe yes, and you can always come up with a complicated way of counting the words and doing n number of things out of it. But for our case, for the sake of simplicity, we are just going to remove it. We don't even care about the names over here. Whether the other things over here will matter much more than the name, definitely. So what you could do is, Sudeep, if you are interested, what you could do is try to come up with the married, unmarried column, based on the names column and see if you get better results after the class. Okay. So Sudipto says that because you have in the name, you have, if you have two names, Mr. and Mrs. and so on, if you detect a pattern like this, you can have another column over here saying that they are married or not. And in that sense, that might be a more indicative or much more meaningful way about using that name feature over here. But name feature right now in its raw form doesn't make sense to us. It will just add noise. Okay. So I'm just gonna go ahead and drop it from our data set over here. So I don't even want the names. So I'm gonna drop name over here. And I want to drop this column. So I'm gonna say access as 1. Okay. So now name is gone. Rest everything I'll take as is, all the features and all the target as is. And what I'll ask you to do as a homework is check which features are more contributing and which features are less contributing to the survival. Okay. So right now we'll take everything else, but the names will just drop it. Okay, so let's do a df.describe over here as well to see some statistical properties of our data. You see that we have 887 number of points, the mean of survived. So if you do 1010, it is coming out to be 38. So it seems like 38.5% of these values are ones, right? If I'm not mistaken, correct me if I'm wrong over there. If you have a lot of 10s and you see the mean is 38.0.385, does that mean that the chances of surviving or the mean value over there is, does that mean that there are 38.5% who have survived? Correct me if I'm wrong. Okay. And these are the quartile ranges. Because this is binary values, it doesn't make sense to look at the interquartile ranges. So it's either 0 or 1. The passenger classes, the parents, the fares, and so on. Okay. So the mean fare over here seems to be 32. And the mean is 0. Someone is going on the ship without paying anything, and someone has also paid 512 euros or whatever. Okay. All right, so I want to do some initial visualizations on my data set over here. Okay. And note over here, we have a lot of features that we can visualize. I'm going to select 2 features because in a 2D space, at max, I can visualize 2 or 3, right? More than that, it will start getting confusing and our visualizations won't make sense. So I want to visualize a few features over here. And based on what I think, you could select any other 2 features as well. I think that the age and the fare of a passenger will be determining factors. It will much matter if they have survived or not, right? So if they are young, they might survive, and if they have paid a lot of money, they might have survived as well. So I want to plot the correlation between these 2 things over here. I want to see I want to plot it on a graph and see the people who have survived, what is their age and what is the fare that they have given, and also people who have not survived, what was their age and what was the fare that they have given. So can you think of a visualization that might help us do that? Go ahead and try it out. My task over here is I want to do some initial analytics or initial visualizations from my data set. So I want to visualize how the age and the fare is affecting the survival. So can you do some initial visualizations for me over here using this data frame? And you pick the visualization of your choice. If you want to draw a pie chart, do that. If you want to do a histogram, do that. I won't limit your possibilities. At the end of the day, you should be able to see how is the age and the fare affecting the chances of survival. Okay. Guys, let me know what you are trying, and if you have got stuck somewhere, I'll obviously be doing it after, once you have tried, but I want you to try it out yourself so that you explore the possibilities which are out there. Okay. If I tell you the answer, you'll be limited from what I know. I don't want you to do that. There is obviously a lot more to explore than what I can tell you itself. Okay. So Sudipto, as I said, there is no right or wrong answer to this. Try it out. As long as you are getting a sense of what is happening, it's good, right? Because in a lot of real world scenarios, you will be stuck with, I want to find out something, but what visualization tool do I use? And you need to use things that make sense to you. All right, so Vibha, as long as you are getting a sense of what is happening and how are these two parameters affecting, you should be good over there. Okay, and there are n different ways of doing it. If by looking at the graph, if you are able to find out how the age and the fare of a passenger is affecting their survival rate, then it is good. From what I see in your plot over there, I don't think you will get a good sense of from what you have done, but it is good that you tried. Also try in the sense of you are having constant colors over there. And right now, the only two parameters that I see that you are using is the age and the fare. Nowhere you are using the survival. So how will you know the passenger has survived or not? With just the two things, the age and the fare, you need a third axis or dimension somehow, which will give you the ability to see if they have survived or not as well. Do you see? And when we were doing our data visualization class, I had spoken about a few things that we as humans look at when we are trying to interpret things. So one was the shape, the size, right? What else did we speak about? Right? If you have the shape of the bar or the size of a bubble, right, that will give you a sense of that will add a dimension to your plot. When we are doing bar graphs, column charts, we are looking at the size of that graph, right? You could also look at the size of a sphere. That will add a dimension to your plot. So think about what other elements are there that will add a new dimension to your plot. Yep, Nitesh, that should work. And what is your interpretation from those graphs? So guys, over here, how many dimensions do I need to plot? And when I say dimensions, it doesn't only mean, don't think in 1D, 2D, 3D, and so on. Okay. So when I say dimensions is how many parameters, how many features. So how many features are we trying to plot over here? So number features, how many do we have? 3. Okay. So a bar plot, how many features does it will help you to do that? A bar graph. When you have a normal column chart or a bar chart, how many features does that help you visualize? 2. Right? And most other charts, line charts and those things, if unless you add a third axis over there, a regular bar chart will give you two features that you can visualize. Okay. So one way is to either do it in a 3D space, right? So if you have, imagine a 3D graph, in that sense, you can do 3 dimensions, but it is not so intuitive enough to understand and interpret those things from a 3-dimensional plot, which is shown on your 2-dimensional screen, right? So what we could do is use other features like shape of something, the color of something, to add that third dimension to our plot. Okay. So whenever you find yourself with a case where you're trying to visualize more than 2 features and you want to add another element to it, try doing it with shape and the color. Okay, that will give you a better sense of what is happening. So in this case, we'll use color over here, and the color we'll use for the survival or not, and the other two axes we already know, the age and the fair. Okay, that will give you a good sense. Either you could do that, or either you could do two bar plots. So because we have two of these things, but that will not give you both of them in the same graph. So if you do two plots individually, then you could do age versus survival and fair versus survival as well. Okay, but if I want to see everything, how everything is correlated with each other, I should do it in one graph. That will make it more clear on how is the relationship, right? So let me go ahead and do that over here. So what I'm going to say over here is df.plot, and I'm going to do a scatter plot over here, and there is no right answer to this. As I said, feel free to use other ways. I'm just giving you some techniques on doing this. So I'm going to use on x-axis, I'm going to use age. On y-axis, I'm going to use the fair. The color for this scatter plot I'm going to use is the survival or not, whether they have survived or not. Okay, so this is the column survived, right? And then in the color map, I want to say the red, white, and or the blue, white, and the red. Okay, so you can look up the documentation of plot.scatter, and they'll have different color maps on with what color you want. I'm over here, I'm saying have the blue, white, and the red colors in my scatter plot. Okay, let's see how do we get, what do we get. Okay, so we have got a scatter plot over here. On x-axis, I have the, let me also make sure that I have over here. Okay, so on x-axis, I have the age, right? And on the y-axis, I have the fair. This is what it is shown. On y-axis, I have the fair, and I have the colors red as people surviving. So survived is 1 over here. So this is red, and the blues are the people who have not survived. So from this graph, is it easier to interpret what is going on over here? Can you tell me, is there a correlation do you see in the people who have survived in the fair? So are there more red dots going up than they are at the bottom? So guys, are you trying it out first? Let me know once you have done over here, and answer me if you think that the fairs, as you increase the fair, you are seeing more red dots over there, and there are more blue dots at the bottom, at the very bottom of our chart. So Nitesh, there are different color maps which are available in plot.scatter. You can go and look at the color maps. The BWR is blue, white, and the red. Okay, you see the scale over here, blue, white, and the red. Let me know once you guys are done. And let me know if this graph makes sense to you in terms of when you're trying to visualize how is one feature affecting the survival rate. Are you be able to get some interpretations out of it? And for the age, we are not really sure. There are some lot of young folks that you see in this region of the graph which have survived. But besides that, there is no strong correlation that I see in terms of age. All the red dots are pretty evenly distributed along the x-axis over here. But the blue dots, you could clearly see that they are now over here, most of the old folks, they have not been able to survive except for this smart gentleman or lady. Yeah, so most of the kids over here, as you see, there is only one or there are few red dots, but most of them have been able to survive. Okay, so that was our initial now understanding of the data set. Now let's try to do some machine analysis or machine learning on it, because clearly the rule based method is not going to work for us, right? If we just try to come up with a, let's say if this was such that all the red dots over here were in this region of the graph, all the red dots over here and all the blue dots are over here in this region of the graph, do we even need to do machine learning? I hope you guys are seeing my pointer on my computer screen, right? I'm asking if all the red dots are in this region of the graph, okay, and all the blue dots are in this region of the graph, do we even need machine learning? And why do you think so, Imanshu? I'm saying that from the data set, 100% of times you see that everything is, all the red dots are over here. Everyone who is, or maybe all the blue dots are over here. Everyone who has paid less money and who are young, they have not survived. Everyone in this top region who have paid high amount of money and who are adults have survived. So everything over here, there is clear separation. Do we even need machine learning then? Why do we need machine learning then? We don't need it, right? You can simply write an if else statement and then give answers 100% of times correct, because it's a past event as such already. Everything that, nothing new is going to happen to this data set, and with 100% of the times you will be able to come up with the right answer. Then why go with something which will give you 90% of times accurate answer? But the fact is, it is not so obvious. All these points are scattered around, and there is no guaranteed way of saying whether you will survive or not based on any two features. So you can try different features as well. If you find some features which are guaranteed to give you the right answer, then maybe you should know, you don't even need machine learning then. Okay. All right. So that is one important thing. Just because you know machine learning, that doesn't mean that you always need to use machine learning. And this is where a lot of people fall prey to, especially in our world of software, and where our clients are asking for fancy new implementations, or fancy uh, algorithms in our programs, where something could have been easily done with a few lines of if else statement. I have seen that so many different times in when I was working in terms of in the industry, where people would ask for machine learning algorithms or machine learning elements in their software, even when there was no need of it, and they would ask to do that to us with and when we ask them how many data points do you have, they'll say that I have 15 data points or I have 100 data points, and that is useless. If you, unless you have 10,000 or even more points to work on, trying to put machine learning, implementing machine learning algorithms over there is just a waste of time. Okay. All right. So let's come over here. Let's come back to Titanic, and let's try to do the same things that we did yesterday. The first thing that we did yesterday is separated out our training and test data set. And even before that, we separated our X and the Y axis, right? So X over here, what is the dependent, or what are the features over here? You already told me what are the features, that all these are the features that we are going to use. And this is our, the survived column is our target. Okay, so I'm going to separate my X and the Y. So X, what I'm going to say over here is df dot drop survived, and from axis 1 So if I do df dot drop on axis 1, what I'm saying is remove this survived column, because all my features are all these things, right? So all these are my features, and I don't want this thing over here. And on the y-axis, I can say df of survived, or the y is my target, right? So this is my target variable, which is df dot survived. X is my features, which is everything except the survived. Does that make sense? So if I say X, I have everything except the survived column. And if I say Y, I have my survived column over here. Okay. Let's separate our training and test data points over here. Now, this time I want you to go ahead and find out, there is also a method. Yesterday we were counting the number of points. So over here, what you could say is X train comma Y train equals to how many points do we have? 887, and you can take 80% of 887, do that math and come up with those things just like we did yesterday. Or you could also use a package from scikit-learn that allows you to do that. Can you go ahead and find out what package from scikit-learn can be used to separate our training and test data points? So I want to say X train comma Y train and Y test Y train comma Y test is equal to something from scikit-learn. What will you give it over here? So not mean squared error, Vibha. Go ahead and search online. We haven't used this yesterday. Which method from scikit-learn can we use to split our training data into training and test data points? And look at an example and try to use it in your program. Yes, Piyush, you could use that. So go ahead and try it out. So Sudipto, what I'll do is first we'll do the first pass without doing anything. And what I'm going to ask you to do is try to improve the accuracy using techniques like what you mentioned. All right, guys, let me know once what you are trying and if you're getting stuck somewhere. All right, guys, so I'm not sure if you already got it, but let me go ahead and do it for you over here. So what I'm going to do is let's go ahead and see how would I go about searching it. So I'm going to say split data set scikit-learn, and this is the hint that I gave you that you should use scikit-learn for that. And as you see, the first thing that comes up over here is the model selection dot train test split method. This train test split splits arrays or matrices into random train and test data sets, right? So you could do that. And here's an example: train test split. You give y shuffle equals to false, or you could say x train x test y train y test equals to train test split, and your x, the y, and the test size. So let me go ahead and use that over here. So let's come over here and x train y train x train y train, or maybe it's x train and y. Let me copy it from here. X train and x test, y train and the y test. Okay, so x train and the x test and the y train and the y test. Okay, so it should be this guy. And what is my x over here? X is small x, y is y. Test size, let's keep it at the 20%, right? So if you want 20%, you should say 0.2. Random state as 42, you can ignore it if you don't want to shuffle your points. What this is going to do is shuffle your data points internally. So every time you run this, you will get different set of train and test data points. Okay, if you want to do that, you could use it, or if you don't want, you could say shuffle equals to false. Okay, in this state, I am going to use my shuffle. So this will internally shuffle my training test data points. Every time I run it, I'll get different values of accuracy and so on. Okay, so I'm just be aware that this is why it is happening. A lot of people ask me, why am I getting different values of accuracy when they have used a train test split in the top? Every time you run it, it is shuffling your data frame and to select random train and test data points. And obviously you will get different values of accuracy if you have different values of train and test points. Does that make sense? Does everyone understand? If you run a train test split method from scikit-learn, and by default the shuffle is true over here, right? So by default it is gonna shuffle your data frame, right? So default value is true over here. Do you see this? If you don't want to shuffle your data frame, you should say default equals to false. So a lot of people ask me that. So something that you should be aware of, that if you're using train test split in your code, then it is going to shuffle your data frame, and every time you run your program, you'll get a different answer for your accuracy as well. Okay. All right, so let's make sure we are getting everything correct. So let's say x dot shape over here, x train dot shape. Now there is some issue over here. Okay, I need to import this first. So let's go over here, and I'm gonna say, let's see, and just note how I go about importing it, and you might have your own ways, but let's just look at the way I import things. So I'm gonna say import, I copy paste from there, and I know that from sklearn.model selection there exists this thing train test split, so I can say import over here. Okay, so this is how I go about doing it. Everyone has their own style. Okay, so I imported that. Okay, so from sklearn.model selection, import this thing, then I can run everything else. And over here now, as you see, xtrain.shape, we have about 709 points in my training data point. Okay, in my training data. Okay, so today we are gonna build a Gaussian naive Bayes model, just like we did before. We were using linear regression model. So today I want you to build a Gaussian naive Bayes. And what is difference between Gaussian naive Bayes and a simple naive Bayes? Where Gaussian naive Bayes will be used for parameters which are continuous in nature. So over here we have parameters which are continuous. So Gaussian naive Bayes will just work for your categorical features. Over here I have things which are continuous in nature, right? So age is continuous, the survived, and when you have both, then you have a choice. Either you can go with Gaussian naive Bayes or simple naive Bayes. Okay, so I'm going to use a Gaussian naive Bayes over here. And again, everyone understands why are we using a Gaussian naive Bayes model. A naive Bayes model can be used for categorical features, like which is yes or no, or what class, first, second, or third. But we have continuous features as well. So in that case, you could use either of those things, and you can try it out with both. So Gaussian naive Bayes from scikit-learn, let's go ahead and import that. So again, I'm going to import this thing. I'm going to copy this, go over here, go to my code, and I can say from sklearn.naive Bayes, import Gaussian naive Bayes. Okay. Again, run this, come over here. Let's create a Gaussian naive Bayes model. So let me paste that again. This is the class. So just like yesterday we were doing model equals to linear regression, today I have done model equals to Gaussian naive Bayes. Okay, nothing different. Now go ahead and use the methods from the Gaussian naive Bayes model to give it our training data set. We have done this yesterday. Can you go ahead and provide our training data to this Gaussian naive Bayes model? Look at the documentation over here. Let me paste this for you. This is the documentation for the naive Bayes model. And go ahead and you provide our training data to this class, this object over here. And there is an example given over here. So I want you to give our X and the Y to this model. How will you go about doing it? So guys, we have done this yesterday. Can you tell me what method are we going to use to provide our training data to the naive Bayes model? And please be sure that you are active in the class. I haven't heard from you guys in a while, so let me know what's going on. Yep, go ahead and use the fit. Try to do that. Okay. Let's go ahead and do the fit method. Use the fit method over here. Fit. And what should I give over here? Yeah, that is fine. Just let me know what's going on so that I don't think that you guys are lost somewhere. So fit takes in two things. We have seen this yesterday. Look over here. Fit takes in two things, the X and the Y. And what should we give over here? What is the X that we should give? Should we give X train, X test, Y train, Y test? We need to give all our training samples, right? So all our training stuff is in X train and Y train, right? So this should work. Let's see. Yep, seems like we were able to build the model. It was pretty quick because we hardly have any points. So 800 points is nothing for our compute power that we have got today. All right, so everyone has their model created and use the fit method to give their training samples. Everyone over here. All right, so let's say now we want to get the accuracy of our results. All right, so the first thing before we do the accuracy, one small thing, because a lot of people get confused with this. So let's say if I want to make predictions on this now. So how do I go about making the predictions? What method do we use from here to make the predictions? Yeah, model.predict, right? And we give the here it is model.predict. You give all the x's and you'll be able to make the prediction. So essentially what you should do is, let's say if you want to make a model.predict, right? So what you could say is, then if you want to see if someone has survived or not, you should give it in this form. Now you could say, now look at all our features over here. So the P class over here, the passenger class, let me look at it over here actually. So the passenger class is 3. Then you have the gender. I think 1 is for males and 0 is for females. Then 22 siblings and parents, children abroad, right? And the fare. So let's say if I take this example over here. Okay, the first example I'm taking, and let's see what do we get. Model.predict. Okay, so I'm gonna use this. So what I'm saying is, you need to give it in the same sequence as your input features are. So I'm saying the passenger class is 3, the gender is 1 or whatever that is, right? So male or female, 1, I think it's 1 is for male. Then age is 22, spouse and parent children abroad is 0, and the fare is 7.25, right? So based on this, let's say what should be my prediction. Okay, and let's see what do I get. And we have an invalid syntax over here somewhere. What am I missing over here? Yeah, this guy. I think it's 22.01. right? So let's see if this works. And our prediction is 0, which we think that it is that they are not going to survive, right? And as you see over here, the actual was also 0. That means that we are making the right prediction. Let's say if I increase the fare over here, let's say if I say the fare was 500, and we know that people who were giving high fares, I think they were surviving more. So if we say 500, now our prediction is 1, that our passenger is going to survive. Okay. So do you see how can you make predictions from the model that you have built now? So try it out and let me know. You can change these things and you can try to come up with, now let's say we also know that there were a lot of people who have very less age. They had survived as well. So let's say if the cost was not so high, if they had not paid not so much of money, they paid only $50 or euros, and their age was very less. So what was the age over here? This is 0, 3, 1 and 22. So 22 over here, if their age was very less, let's say their age was only 3 years. Now what is our prediction now? We still think that they are not going to survive based on the other things. Okay, so maybe we're still not so confident about the age. With the age, we are not getting much things over here, right? So whatever age we keep, I think it's not affecting a lot. If the age is too high, then it is still low. And whatever age we put over here, it seems like our model is just ignoring it. Okay. So visually, we thought that no, from what our understanding is, that we want people who have less age to have more survivals. But if you count the number of points, there are more red points in this region as well, right? So I guess it doesn't matter much. If you inspect it, logically think the total number of points which are scattered everywhere, those are even more than what are just concentrated in this region. So to say that people who have very less age, only they have survived, I don't think that will be, if you calculate the probabilities, that might not be true. And that's what our model is doing. It is ignoring the age parameter altogether. But the price, as you saw, if you pay 0, our prediction is 0. If you pay $500, your prediction is 1. Okay. All right. So the last thing that I want to do is calculate the accuracy of our model. And over here, again, you have a method which will allow you to do that in just one line on how accurate were we. Can you look at the method names over here? And can you tell me which method can we use to get the accuracy of this model? Yeah, model.score. And it says that it takes again X and Y. And these are the test data points. So we need to give the test data points of our the testing points, right? So over here, model.score, X test and Y test. So if we do this, we are getting accuracy of about 73%, which is not that great, but not that bad either, right? So with little efforts, we were able to build a predictor which is correct 73% of times. And this number might be differing for you. And can you tell me, based on what you have heard me saying, why this number might be different for you? If you are getting the same results, that is good. But if you have not used the random state over here, if you have a different random state, your numbers will differ. So if you don't use this, right, so our answers might differ then. So now I have 77%, which is even great. Okay. So if you want to know, now compare two methods, then maybe what we should say is shuffle equals to false over here. So if you say shuffle equals to false, now that will make sure that we are not shuffling a lot. And we get a sense of, now we can compare two to three different techniques. Okay. All right. So that's it for today's class. I hope you enjoyed working on this data set. My homework for you is to find out different ways you could use other uh, classifiers from scikit-learn to get better predictions. So can you try out different models on this data set as well? And the other homework that I have for you is to also perform a classification on the email spam data set. So let me make sure that you have the link to that. Okay, so give me 1 second. The email spam data set, it should be on your course page. So if you go to your course page, over here. So this is your course page, right? And naive Bayes classifier, go to the homework. And in this homework, you can download the data set, download the email spam classification data set from here, right? So let me make sure the link is working. Okay, so the link should be working over here. So this is the CSV file that you need to work on. And this is a raw file. So there might be some problems with the file encoding and so on. So I need you to deal with that, okay? This is as is, I haven't done anything. This is a data set which was available online and I just put it as is for you to work with. So there might be some problems with the file encoding and those things. You need to learn to how to deal with those problems. The first column over here is a ham or a spam. It's just a fancy way of saying that it's a spam email or it's not a spam email. So hams are not the spam emails, and you need to look at all the text which is inside your emails, and based on that classify whether these emails are a spam email or they are not the spam email. Okay, so everyone understands the problem statement. Pretty simple, only two things over here. One feature set with one feature column which is your text, and one target column which is your ham or a spam. Okay, can you guys try it out? You have the homework on your course page over here. Okay, great. All right, then I'll see you next time on next weekend. Till then, make sure that you are connected with me on WhatsApp. For some of you, your foundations course will be coming to end next weekend. So if you would want to continue with the rest of the class, please make sure that you reach out to me and ask how can you continue working with us. Till then, goodbye. I'll see you next time. If you have any questions, please feel free to reach out to me on WhatsApp. Okay. Goodbye.